Here, I will introduce the Analytic-Splatting, Anti-Aliased 3D Gaussian splatting via analytic integration. Anti-aliasing is a long-standing challenging task in computer vision and computer graphics. Anti-aliasing aims to remove the artifacts, such like the moire and jaggies in the rendering results. The key to anti-aliasing is to handle the pixel's footprints, which means we need to find a correct pixel corresponding domain in the texture space and calculate the average expected shading value of the corresponding domain as the shading result of the pixel. Supersampling scheme tends to increase sampling bandwidth and capture more high frequencies, while mipmap scheme pre-filters the texture and store a larger texture pyramid for anti-aliasing. Now, mipmap is the most widely used technique for anti-aliasing. Before rendering, we conduct pre-filtering establishing a pyramid of the texture. During rendering, we can easily get the nearest index of the texture pyramid and interpolate for each pixel. Let's revisit 3DGS, so how to achieve anti-aliasing of Gaussian signals. The artifacts in 3DGS area are caused by the fact that it only considers the response of Gaussian signals at pixel centers. Exactly, anti-aliasing in 3DGS aims to accurately reconstruct the window response, which is the Gaussian signal integration within each pixel window. However, the CDF of a Gaussian is an error function, which is hard to calculate and not well supported. Supersampling, also Monte Carlo sampling, and pre-filtering are suitable ways to solve this integral. In this work, we find a great way to approximate the CDF of Gaussian signals and then get the integral. In this work, we find that the logistic function has similar properties of the CDF of a Gaussian signal. They have the same limits and they are S-curves through 0.5. Thus, we use a logistic function to approximate the CDF of a standard Gaussian signal. To verify the approximation, we analyze the approximation error. The results show that our approximation performs well. For different standard deviations, the error remains within a small range for both the approximated CDF and the one-width window response. Our scheme outperforms other schemes to approximate the response over the one-width window, especially when the standard deviations of Gaussian signals become smaller. Then we apply this scheme in the 2D case, shading pixels using 2D Gaussian in the screen space. Sadly, we have some problems. There exists a correlation term that makes this integral hard to solve. Fortunately, eigendecomposition is our good friend to remove the correlation. Intuitively, we can slightly rotate the integral domain to make this domain align with the eigenvectors. In this way, the integral of a 2D Gaussian can be decomposed into the product of two integrals of a 1D Gaussian. Finally, we just need to apply the approximation here and achieve anti-aliasing. Now, we reformulate the expression. After eigendecomposition, we get the eigenvalues and eigenvectors of a 2D Gaussian signal. For a single point, like the pixel center, the response can be decomposed into the product of two 1D Gaussian signals. Further considering the 2D window integral, the integral can also be decomposed into the product of two 1D Gaussian window integrals. Finally, we approximate each 1D Gaussian window integral using the conditioned logistic function and get the 2D window integral results. Here, we have several examples to show that our approach has better anti-aliasing capability, giving more details and better fidelity. Please check our paper and project page for more results, code, and demo.